Yeah, this is the subject today. We're going to pick up where we left off last time and talk about the book that William Gilbert published in 1600. Now, last time we started with the earliest discoveries about electricity and magnetism that were made in ancient Greece. And I mean, the Greeks didn't know the subjects of electricity and magnetism. I mean, as we understand those ideas today, for them, what electricity meant was just this strange power of amber to attract straw and fur and hair, that kind of thing, after you rubbed it. Now, what they knew about magnetism was just that there was this strange power that this one particular kind of stone, lodestone, had to attract iron. And that one lodestone would attract or repel another lodestone depending on how you oriented them. So that's what the ideas meant to the Greeks. That's what they knew. Now, by the time Gilbert writes this book, a fair amount more is known, and he's really he approaches the subject very scientifically. I mean, he does quite a few experiments. So this is the first real scientific investigation of electricity and magnetism. And if you think about when this book came out, when Gilbert was doing his work, you can relate it to what we learned last year about, because Galileo, Kepler, they're doing their work at the same time. Okay, so science is really getting started at this point. Now, I want to give you highlights from this book today, basically. Now, the first one we talked about last time, and that is that Gilbert discovered that the Earth is a magnet. The Earth is a giant magnet. And that's what explains the way the magnetic compass worked. People had figured out long before this that if you take a thin, long piece of lodestone, or if you use a lodestone to magnetize a thin piece of iron, then it will always point in the direction of north. And I guess, Mr. Van Dam showed you that earlier, and you saw how a magnet, if you set it floating on water, will orient itself in that north-south direction. Now, Gilbert also realized something else. He realized that it's not just that the magnet will orient itself north-south, but if it's free to pivot in the vertical direction as well as horizontally, it will point down toward the Earth. And one way you can show this is if you take say a thin magnetized piece of iron, okay, and you put it through a piece of cork, and then you submerge the whole thing in water. So if you take let's say you have a glass of water, and you have a piece of cork with a magnet through it. Well, it will not only point north, but it will point down toward the Earth too. And Gilbert realized when he saw this, I mean, now, in order to do this experiment, of course, you have to arrange the magnet and the cork. The combination of the two have to be the same density as the water, right? Because you don't want it floating on top, and you don't want it sinking down to the bottom. But if you can get it about the same density as the water so that it floats in, so that it submerges in the water and just floats in equilibrium there, then you'll see this effect. Now, Gilbert realized that, well, this makes perfect sense, given his idea that the Earth is a magnet, and that's what's causing this effect. Because he figured, well, what would you expect this thing to do if you went all the way up to the North Pole? How would this point, Troy?
Directly down?
Yeah, point directly down to the magnetic pole of the Earth. Now, given that, if you went down to the equator, how would you expect it to point?
Like about parallel to the...
Exactly. So it would be horizontal. Now, where Gilbert is in London, he sees an intermediate situation where it points partly down to the ground, but still has a horizontal component. Okay, so this just reinforced for Gilbert the idea that the Earth was a magnet. Now, this is called, by the way, the magnetic inclination. And it just refers to this effect of the compass needle or the magnet, the angle it makes with the vertical, the degree to which it points down to the ground. Okay, now, Gilbert also made a study of electricity in this book. And one of the things he did that turned out to be enormously useful was he invented a new kind of instrument to investigate electricity. Before, all people were doing were taking pieces of amber and rubbing them and then seeing if they could pick up little pieces of straw. Okay. But what if, if, for instance, you tried to test whether or not something besides amber might be electrical, and you picked some substance and you rubbed it and it wouldn't pick up the straw. Well, I mean, you're left in a situation where you're not quite sure. Maybe it really does have some of that electrical power, but it doesn't have as much of it as the amber. And it doesn't have enough to pick up the straw, but if you had a more sensitive way of testing whether it had any of this electrical power, maybe you could find that it did. Well, so Gilbert wanted a more sensitive way to detect electricity, and that's exactly what he invented. The device that he invented is called the electroscope, and it's very simple. All he does is if he takes the one he describes in his book is actually made of metal. It's just a long, thin piece of metal, and it's balanced on a pivot. And it's free to rotate in the horizontal direction. Okay, so what he does now is he rubs the piece of amber and he holds it, say, to the side of this. I mean, if this were, if I rubbed this and then held it out here to the side, you'd see this metal needle swinging toward it. And if if this pivot has very little friction, and so it's very easy to swing, and this is a light object, it's much easier to get something to just pivot and swing than it is to pick something up. So basically what he's got here is a much more sensitive way of detecting the electrical force. And and furthermore, he can actually see more clearly how the force depends on distance. If he takes, say he rubs a piece of amber and he holds it 2 inches away, and he finds the needle slowly swings toward it. Well, if he holds it 1 inch away, he finds the needle moves toward it more quickly. So he can see, at least qualitatively, how the electrical force depends on distance. And I mean, he discovers that yes, it does depend on distance, and the force is greater if the objects are close together, and it's weaker if they're further apart. Okay, now this led him to an important discovery. Once he had his electroscope, he could start testing. He started testing a whole bunch of other materials, not just amber. And he discovered that many materials have the same electrical power as amber does. In particular, he found that if he rubbed diamonds, well, a whole bunch of gems he found worked. If he rubbed diamonds, opals, sapphires, they would all, and held them up to his electroscope, it would cause the electroscope to swing. So it's not just amber now. Yeah, Dan?
Which of the materials was the most strongest of them all, though?
Well, amber had the strongest effect, which is why the Greeks first noticed that the electrical power in the amber. But the others clearly swung the electroscope, and so they had the same effect to a slightly lesser degree. And let me see, he discovered glass worked, rock crystal, sulfur, so a whole bunch of materials now. Now this was an important discovery, because if all electricity is a strange property of one material, and not even a very common material. I mean, it's not like there's just big chunks of amber all around us, right? So if I mean, actually, amber, I don't know whether I told you this last time, is fossilized pine resin from a type of pine tree that doesn't even exist anymore. So it's not the most common material in the world. And if all electricity is a strange property of this one material that comes from a pine tree that doesn't even exist anymore, then electricity wouldn't be very important. But in fact, Gilbert shows that you could rub all kinds of materials. I mean, really most of the materials out there that you can get your hands on, if you rub them for a while and hold them up to his electroscope, it'll cause it to move. So now electricity takes on a lot more importance since lots and lots of materials have this property. Now, Gilbert did find some materials that he couldn't seem to make his electroscope move at all. In particular, metals would not move his electroscope. So he came up with, he divided materials into two classes, what he called electrics versus the non-electrics. So the electrics have the power of that amber does, and they include the gems, so diamond, sapphire, opal. Let me see, sulfur, glass, yeah, rock crystal. Yeah, right. I mean, they didn't have a lot of plastic back then, but and then there's the non-electrics. And for example, I think that Gilbert actually had a few other materials that I think he classified as non-electrics, but certainly the metals. Okay. Oh, one other thing. Remember that one other way that the Greeks would have restricted their view of electricity was that, I mean, not only was amber the only substance they knew that had this power, but the only thing they talked about amber attracting was straw and fur. Okay, they didn't know that it would attract lots of other things. Well, Gilbert's electroscope is made of metal, so clearly the amber will attract metal. And he found a whole bunch of other materials that it would attract. Yeah?
Did you say metals don't attract them?
Oh, he couldn't get the metal to attract the electroscope. Okay, so if he rubbed a piece of metal and held it up to the electroscope, it wouldn't attract it. But the electroscope itself is metal. So if you rub a piece of amber and hold it up, the metal electroscope will swing toward it.
So things will attract metal, but metal won't attract them.
But metal won't attract that. That's what Gilbert, that's what his result was.
So
Now later, we're going to figure out that Gilbert didn't have the whole story here. But this is how far he got in his understanding. Yeah, I mean, he could see, yeah, the metal would swing toward the amber, but he couldn't get a piece of metal once he had rubbed it to attract the metal electroscope. Okay, so, but he found that, I mean, this electroscope didn't have to be metal. It could be all kinds of things, and it would still work. I mean, if it were wood, it would swing. He found that these electrics would attract, you know, a whole bunch of materials. Wood, metals, leaves, even water. If you had a stream of water and you had and you held a piece of amber up to it that you had vigorously rubbed, you could see the stream of water deflecting a little bit.
So
So
it would go away from it?
it would go toward it. Yeah, attract it. See, all these are attractive forces at this point. Okay, the only thing people know about electricity at this point is that it's an attractive force, not Okay, now, so he's making progress. I mean, this is a big step, because now electricity has become a property of all kinds of materials, not just amber. All right, now, let me tell you about a couple of other things that Gilbert did in this book of his. Okay, now, one of the things he did was he refuted some false ideas that people had about electricity. And so that at least clears the way toward discovering true ideas. Now, one idea that people had was notice that, I mean, the amber doesn't do anything if you just hold it up to the electroscope. You have to rub it first, right? Well, some people had the idea that the reason the rubbing worked is because when you rub something, it heats up, right? So some people thought, well, maybe it's not the rubbing here that's important. It's the fact that by rubbing it, you're heating it up. And the warm amber has this effect, but cool amber doesn't. Now, how could you test that idea, Drew?
Maybe put up like a cold amber to the thing and see if it would go off, and then rubbed it and see if it done.
Well, if you just did that, I mean, if you just took a cool piece of amber and put it near the electroscope and then rubbed it vigorously so it heated it up a little and then put it near the electroscope, you would see what people had always seen, that the rubbed, heated amber would attract the electroscope, whereas before you rubbed it, it wouldn't. So that wouldn't answer the question. Selah.
Get two pieces of amber and make one warm and keep the other cool and then do it? Or is that pretty much the same thing?
Yeah, well, how would you make the one warm?
Maybe you could just like put it over the fire or just rub it.
Exactly. If the cause here is really the warmth, well then why can't you just take a piece of amber and hold a candle flame up to it, heat it up, and then see if it attracts the electroscope? Okay, well, Gilbert did that. I mean, he didn't just, throw these ideas out there. He tested them. So he did that and found that if you take a piece of amber and you put it under a candle flame and you heat it up and then you put it next to the electroscope, it doesn't do a thing. Okay, so it's not the warmth alone that is the cause here. Drew.
Maybe it's when you're rubbing it, it causes friction, and that's what caused it.
Yeah, that turns out to be right. The friction is absolutely crucial. It's not the friction just to create the heat. Now, well, so anyway, let me write something down here. Let's call this testing whether heat is relevant. Now this first test that Gilbert did, just holding the amber, say, under, heating it with a candle flame and then putting it next to the electroscope and seeing that it doesn't do anything. Now, does that necessarily convince you? I mean, what if the heat could still be part of the cause? Obviously, what you've proven is the heat isn't the whole cause, because you can have heat and there's no effect. So, you know, but maybe you need the rubbing and the heat in order to get this electrical effect, and so that the electroscope swings. Now, how would you rule that out, Christopher?
You could take a piece of metal and try to rub it and then see if that.
Okay, but how would that address the issue of whether or not the heat was part of the cause? It's whether you needed the heat in order to get the effect. Troy?
You could rub the amber in like a really cold freezer.
Yeah, well that was my idea. Is let's say you take a piece of amber, and you wrap it in something to keep it dry, but then you put it in a bunch of you stick it in a bucket of ice, okay, and you really cool it down. Then you rub it and hold it up to the electroscope. Now the amber is still, well below room temperature. I mean, it's still cold. If you can get a cold piece of amber to attract the electroscope, then that would really seem to eliminate this idea that the heat is relevant. So now Gilbert didn't do that second part. The only experiment he did was the first one I told you about heating it up with the candle flame. But he could have made. Oh, yeah, Rachel. So he could have made this more convincing if he had done both the candle experiment and the ice experiment, but he did reject this wrong idea that the heat was relevant. So Gilbert concludes that it isn't. Okay, now well, there was another people had also put forth an idea of how the amber attracts the electroscope. People understandably wanted to explain this in some way so that it didn't seem quite so magical. And so the idea was that maybe somehow the amber is affecting the air, and the air is actually moving the electroscope or attracting the straw or the fur, or whatever it is. That when you rub this amber, maybe it emits something that causes the air to move in a way that then causes these other objects, the electroscope or the straw, to move toward the amber. And the idea that had been put forth was that when you rub the amber, it emits something that pushes the air out of the way. And then an object like a straw will get sucked into that space because the air isn't there anymore. So trying to explain how this electrical attraction that seems so magical actually works. Well, Gilbert thought, well, if the amber moves by pushing the air around, can you think of a way to test that? Troy?
Do the experiment in a vacuum?
Oh, yeah, that's the perfect way. Unfortunately, This is 1600.
Oh, yeah.
And when was the vacuum pump invented? I told you that actually at the end of last year. Daniel, you remember?
I think it was in the 1760s.
1660 actually, or around there. So it's yeah, it's not for a while longer that that people would have vacuum pumps. But as soon as they did, they actually did that. Exactly what you suggested. Yeah, Nick.
Try it underwater.
Oh, try it underwater. I didn't think about that, but
Give too much resistance.
yeah, it would be harder to try it underwater because you would be introducing a lot of other factors too that might cause you not to observe the electrical force. So, yeah,
If
neat.
we did that, the same thing could make the water move in the same way that makes.
Yeah, I mean, possibly. It might, although someone might argue that, well, this electrical force is strong enough to push the air, but not the water. So that wouldn't be a decisive experiment. What Gilbert thought of was, if you take a candle flame and even a really slight breeze, a movement of the air, will cause the candle flame to flicker. Okay? So if you rubbed really vigorously a piece of amber and you held it up to a candle flame, well, if the amber worked by moving the air around, you should be able to see a little flicker of the candle flame because the air was moving around. Well, you don't see it. So Gilbert concludes that however this electrical attractive force is working, it's not working by pushing the air around. So let me see. Yeah, let me just write air is irrelevant to electrical force. So Gilbert never figured out, how this force works exactly, but he he at least got rid of a couple of bad ideas that people had about it. So that's a step in the right direction. Okay, now one of the most important things that Gilbert did in his book was clearly distinguish the electrical force from the magnetic force. He pointed out, this is 5, right? He pointed out some major differences between electricity and magnetism. And people had tended to confuse these two things because remember when this whole subject started, all that people knew was there were these two things, amber and lodestone, that both had this strange attractive power. And so people just tended to group them together. Well, but Gilbert points out there's major differences between these two. We can't just group the amber effect in with the lodestone effect. And he lists a bunch of them in his book. So let's see if you can tell me what the differences are. Nick.
If you had a long piece of amber, that's magnetized, it wouldn't, no, electric, it wouldn't spin, it wouldn't point north-south.
Right. No, that's true. well, let's just say the Earth is not electrical in the sense that it's magnetic. Let's now, later I'm going to tell you about a way that the Earth really, there is one sense in which the Earth is electrical, but you're right, it's not like the sense in which it's a magnet. So, okay, I'll accept that one. What else we got? Neve?
Magnetism only attracts metal, not anything
Yeah, not even just any metal, right? Iron.
else.
So I mean, that's a huge difference between magnetism and electricity. And that's actually the first one that Gilbert lists, is that electrics, what he calls electrics, attract many materials magnets only iron. Sorry, what do you got?
Electrics don't repel things.
Oh yeah,
They only attract them.
right,
While lodestone will repel other lodestone.
right.
And
Let's put that, let me see. The way that Gilbert put that point was that magnets have poles. Electrics do not. And in other words, a piece of lodestone has, a north and a south pole, and it will, if you bring another lodestone up to it, it will attract one end of that other lodestone and repel the other end. So it magnets have this orientation to them, and the two ends behave differently. Whereas if you just rub a piece of amber, the whole piece of amber acts the same way. Now, you might say, well, what about, let's take a magnet with a north end and a south end, and let's just cut it in two. Okay, now we'll get a situation more like the amber, right? We'll have a magnet with just a north pole and another magnet with just a south pole, right? Is that what we would get? Try.
no,
No, what do we get?
two smaller magnets with north and south poles.
Yeah, exactly. You end up with two magnets. They each have a north and a south pole. So you can't get around this, the fact that magnets come with these poles, and one end is different than the other end. Even if you cut it in two, and Gilbert did this. I mean, he checked this idea. He took a piece of lodestone that was magnetized, he cracked it in two and saw that all he ended up with was two magnets, not, a north pole in one and a south pole in the other. Yeah.
If a piece of lodestone was cracked into many fragments, would there just be a lot of north and south, really small north and south poles?
Yeah, no matter how many, I mean, you can just keep cutting it, and you just get smaller and smaller magnets. Drew.
Well, how would you know? Because even like if you do cut it in half, like let's just say there's a south pole right here, it's still pointing south, but the other side is always going to point north. How do you know that that side is really actually pointing north?
Oh, well, you could, in other words, how do I know, once I cut this in two, how do I know that this end is a north pole?
Yeah.
Well, I can hold it up to this other magnet. Okay, now if this is a north pole, it should attract the south pole and be repelled by this north pole. That's exactly what you see. Sorry.
Why is it like that?
Why is it like that? At this point, we have no idea. It's just the way things are. And it would be a long time before people figured this out. This is tricky. That's why, actually, when I read these scientists like Gilbert and his contemporaries that are trying to come up with a theory that would explain all this, you have to almost feel sorry for them, because with hindsight, I mean, we can look back today, people that have had physics can look back today and see all that they had to know in order to really be able to explain these simple observations that they're making. And it's an incredible amount that they had to know. I mean, they didn't have anywhere near the knowledge at this stage that they needed in order to come up with a theory.
They had no chance of figuring it out.
They had zero chance of figuring it out. They were still trying. But first, you just have to get the basic facts and get clear on all these facts. And Gilbert made an enormous contribution by doing that. Now, let me see. Well, what else? We've got, there are other differences I'm looking for here. So there's one really obvious one that we haven't got up there yet. Do you have to rub a magnetic compass in order for it to work? No. No rubbing required. Okay, well, that's a big difference. So, let me see. Electrics need to be rubbed. Magnets don't. Now there's one I haven't told you about yet that is also really important and struck Gilbert as important, which, oh, it's time? I'm being cut off here. We'll finish this list next time. Big extra credit to anyone that can come up with another good one, though. There's one or two more I haven't gotten to. Hmm?
What kind of extra credit?
Oh, I don't know. I'm just winging it here.
His approval.